fuzz matching. Contrary to chemical etching, it's almost hazard-free, except dead voltage. You can buy one of these, but it's getting really hot just after a few minutes. Plus, what's the fun in that? Instead, we would like to make our own version of solid-state Tesla coil. Let's do it! Although there are only 5 main components in the circuit is far from being easy. The reason for this is large signal. In order to analyze this circuit, we will use LT-SPICE simulator. I have used LT-SPICE. Although the simulation isn't 100% accurate, it gives us insight into how the circuit is working, and it's extremely easy to change values. Another useful tool is coil 64. It can give coil inductance from coil diameter, wire width, and number turns, and vice versa. The circuit is made of 3 parts: simple voltage regulator using Zener diode, LC circuit oscillator, and quarter wave resonator. The first part is quite straightforward. The second part is tricky, as it needs a very accurate curve value. In the third part, you must know exactly your LC oscillation frequency. Now, let's go over the main parts and see why those values were chosen. The 100 picofarad high voltage capacitor and 4 nanofarad plus 4 nanofarad of MOSFET gate are voltage divider. We want gate voltage to be 20 volts, MOSFET max allowed gate voltage, and LC capacitor should get 2000 volts. The 100 picofarad capacitor should be a VIMA MKP high Q capacitor. If a low quality capacitor is used here, it may get really hot even with 2000 volts. There are no restrictions on the 4 nanofarad capacitor. You may use any unbraided one. LC coil is 2.3 microhenry to make a 10 MHz LC oscillator. It's very important to use exactly this coil value, otherwise it won't go nicely with gate ringing. Some minor adjustments are still needed. The RFC coil can be anything between half of the LC inductor value to about 10 of LC inductor coil. If it's too small, too much current will flow through the power supply. If the RFC is too big, not enough energy will get into the LC oscillator. MOSFET IRFP 260N was chosen since it has a lower resistance of 40 milliohm compared to 75 milliohm of IRFP 250. But IRFP 260 was not working on high frequencies of 15 MHz. There, IRFP 250 was more appropriate. All other component values are not that important. Changing their value didn't have any visible effect on the output voltage. The circuit is very sensitive. Less than an ohm on LC path may kill oscillation. LC capacitor is only 100 picofarad. Any wire may add few picofarads. Working with high currents and high voltage creates ground loops. To overcome all these problems, I made a PCB board. This way we will reduce ground loops by reducing wire length. Wires capacitance are constant and don't change. Plus, it's much easier to reproduce. MMC or multi-mini capacitors. It's a way to use multiple low voltage capacitors to reach higher currents and voltages. In our case, one capacitor can withstand 2 kV. So combining two in series will put them far from the danger zone, as each of them will get only 1 kilovolt. Putting another two parallel will bring overall capacitance back 200 picofarad and reduce resistance by a factor of 2. The resonant coil is a tricky one. It's not a self-resonance coil, but a quarter wave. To calculate the number of turns, you should find your frequency from oscilloscope. Convert frequency to wavelength in meters. Divide by 4 to get the length of the quarter wave. From your coil diameter with insulation, you can find the number of turns. Now for the fun part. Once we have all the components, we can assemble it quite easily. Test. Part 1 is simple voltage regulator. Testing part 2, 2 kilovolts point to point plus fluorescence. Testing part 3, plasma flame. Warning: this project uses high voltage and current. Please perform every step with caution. I don't take any responsibility for injury or damaged equipment. Please read many sources before attempting this circuit. Good luck!